All right, so one of the famous experiments in physics, the first experiment that revealed interference of light, it was performed in 1800 by Thomas Young, involved this double slit experiment. So we start with monochromatic light. So we're going to represent it like this. Monochromatic, meaning same wavelength, right? And I'll use red here. Wavefronts can be represented like this, presuming they're equal. All right, so this light is incident on a very, very small slit. Very small slit right there, which makes the light spread out like this. And it makes it have this these curvy wavefronts like this. Oops, I'm using the wrong red. All right, and let's say that's angle theta. So then that light is incident on another slit. Actually, two more slits right next to each other. And these slits are like micron width. So they're tiny, tiny little slits, right? And so these wavefronts are incident on these slits, right? And what happens is you get a similar situation as what happened for, I'll say, slit 0, slit 1, or screen, I don't know. Or we'll call S1 and S2. You get the same situation where they are spreading out from each of these. And as you can guess, those two interfere with each other. So these are two sources nearby each other of monochromatic coherent light that overlap. Kind of like that. So you have this guy, and it's going to be incident on a screen here. The final thing, incident on a screen. And then separately, this guy. Right? So kind of similar thing to what we were just looking at, where it's going to interfere and give this interference pattern on this back screen. And so what we see, what we observe, or what Thomas Young observed in 1800, was he saw a really bright spot, slit, or band, or interference spot of light right in the center. And then he saw kind of more diminished bands. So they kind of like, they kind of are weaker as you go away. Yeah, you can kind of imagine this interference pattern. here, where you go from alternating bright and dark bands, with the brightest band being right in the center. And so these are often referred to as fringes, like a fringe pattern. And it's just the result of an interference of these two coherent monochromatic sources, the ones, from each slit, interfering with each other. So let's kind of examine this from the angles a little bit more instead of this qualitative picture. So let's say we have this is here. I'll redo that. We have here, and here are two slits, right? So this is like S1 and this is like S2. And the distance between them we're going to call D. And we have our if we kind of borrow from geometric optics and treat these things as rays, we have a ray coming out like this to arrive at a given point that we analyze onto the back screen, and this is just an arbitrary point that I've picked here, and so we're just kind of looking at, like, for light to arrive at this point, I'll say P1 or P, this point, what angles must the light have traveled from the slits in order to hit that point, right? So very geometric optics kind of a thing, right? So we have maybe an axis we can define here, and we can say this is an angle theta. We'll call this R, call it capital R, and we'll make this gray so that it's not a physical part of the system. And the same angle can be identified here, theta. And then in that case, this right triangle, right, we can say this is d sine theta. Okay. And this is the screen. All right, and then finally, we're going to identify here to here as being the distance y. Okay, so if this distance r is super large compared to the distance between the slits, right? So this distance d between the slits, I don't know, centimeter or something. But if the distance to the screen is actually like, huge or something, like a meter or something, then the angle difference between these two rays becomes less and less significant, right? If you think, what if the screen rather, is like on the other side of our solar system, and these two rays emanated from two sources that were like a half a centimeter apart. So like the farther out you go, the more and more these two rays appear as parallel. And so let's make that assumption that it's far enough away that these two slit sources, the rays emanating from these two slit sources, are basically parallel. So we're going to say approximately. So it's a similar situation. It's just we don't have to worry about the weirdness of, I'll just go with freehand because it's taking too long. I'm not even going to draw the screen. It's just going to like go off, right? Very, very far. So then we have this going towards some point, and we have this one which is parallel, right? Okay, so R1, R2, R1, R2. All the same stuff applies back here, where this defines a right triangle, and this defines an angle, and this defines an angle. All that we've done is we've made ray 1 at the bottom there parallel by considering the screen super far away. And that simplifies the math a little bit. Okay, and so in that case, then the path length difference between R1 and R2 can be more easily defined. And we can go back to saying that R2 minus R1 is equal to this path length difference here, right? The difference from where their starting points are if they're both traveling parallel. So d sine theta. And we know that constructive interference occurs at integer multiples of the wavelength of light. And so therefore we can say, because we know, basically what I'm saying is we know this for constructive interference, then what we can do is we can just fill this in with d sine theta for m is equal to all those things, integer multiples, plus or minus 3, you get it. And similarly, total destructive interference occurs at half integer multiples. So this would be constructive, and total destructive is given by our plus a half. D sine theta is equal to m plus a half, right? Where m is the same thing. Okay, so that's simple enough, right? We just basically made a really easy approximation if you have those slits really close to each other. It's a pretty fair approximation. So what this means is we can consider this pattern that forms, and we can see now that the brightest center, the brightest center band or fringe here is m equals 0, right? So that's when they're both heading towards. That's like back in our interference pattern when we were looking at point A and the path length was completely equal. And it's the brightest spot here. And so that corresponds to m, I'll write it here, m equals 0. And then the dark bands on either side, so dark, dark, m equals, we can say minus a half down here, and m equals plus a half there. And then the next band is m equals 1, and here, right, m equals negative 1. And then m equals negative 1.5, m equals negative 2, right? So you can see these interference fringes that appear on the screen are just defined by the periodic constructive and destructive interference from the path length differences from the two sources. That's all that it really comes down to. And in terms of this value y that I identified here, to find the distance between the fringes, it can be shown, we won't show it, but it can be shown that for small angles at least, the fringe separation y is a function of m, right, because it matters which fringe you're talking about, is given by r, that's the distance from the slits to the screen, times m wavelength divided by d. Right? So that's just a nice relation we're going to just take at face value there, and not, for once, derive. Boop. All right. Next, we're going to talk about intensity in interference patterns.